Yeah, so we should be good to begin now.
Okay, so can you hear me, see me?
Yeah, all good. All yours now.
Okay, so hello everybody. Welcome to the webinar where we will be talking about memoization and dynamic programming. And my name is Michal Forisek, or maybe better known in the programming contest community as misof. And yeah, tonight I will be your host and I will be the one talking to you about these concepts. So first of all, before we actually get into the topic, let me mention that at Top Coder, we have also prepared not just this webinar, but also a practice contest. The practice contest contains 10 problems from the history of Top Coder that are somehow connected to dynamic programming. The contest will be available for, I think, 23 hours after this webinar is over. The difficulty of these problems is varying. They start somewhere at the Top Coder Division 2 medium problem, and they are all the way up to the Division 1 medium problems or something like that. So something from very, very early intermediate to reasonably hard problems. And if you want to take part in this practice contest, then at any time, including right now, you can go to the Top Coder arena to register for the contest. So that being said, let's start talking about dynamic programming. So this is a very broad topic. This topic has very many different facets, and there is a lot to talk about. So there's definitely not a chance to do everything in this single webinar. So I will try to split my attention between two main things. In the first part of the webinar, we'll start with stuff for the absolute beginners. So we will start at the very beginning, and we will go through all of the concepts, and I will explain my particular way of looking at dynamic programming and thinking about these problems. And once we got this out of the way, and once we have talked about a few of the very easy problems and how to solve them, and I will try to actually implement some of the solutions for you in real time so that you can see how it is done. Well, once we are finished with this part, then I will talk a little bit more about the more difficult concepts and about, for example, differences between DP and memoization. I will see how much time we will have left. So when we are talking about dynamic programming and memoization, it's actually better to start even one step before that. So let's not go directly into what these concepts are, what they can do for us, and let's start with something even more basic. So I still remember a short saying that was invented by one of the USECO organizers, that there is no real secret to the design of efficient algorithms. There are only two things you have to make sure you're doing, and they are don't do anything stupid and don't do anything twice. And today, the entire webinar is about the second of these two very simple rules: don't do anything twice. And when we are talking about memoization, one of the first examples of something similar date to the age of, I'd say, 80s in the previous century. And all of us that are working on computers are working on some version of MS-DOS and so on. And people are starting to come up with ideas to create, for example, the first 3D shooter games and such, and games that actually use kind of physics and can rotate the camera. And back then, we didn't have any fancy graphic cards that could do such tricks. All of it had to be computed on the processor. And the problem was that the operations were kind of slow. Adding two real numbers is reasonably quick. But for example, computing the cosine of an angle is maybe 10 times slower, because you need to do several iterations of some numeric process where you compute a Taylor polynomial or something, and you compute it with sufficient precision that you get what you need. And the computers were not fast enough to be able to do all of the computations they needed for each and every pixel on the screen. So the authors of the games and programs came up with a clever observation that a cosine is a cosine. A sine is a sine, is a mathematical function. A pi is a mathematical constant. And the value of these things doesn't change. If you compute the cosine of 17 today, it will be the same result as if you computed the cosine of 17 3 days ago. So what they did is these programs, in order to speed them up, they at the beginning, the program started with pre-calculations of some values. So for example, the program could initialize a table of size 360. And now for each angle in degrees between 0 and 359, it will compute the cosine of the angle exactly and store it in the memoization table. And now if the application needed the cosine of 347, it could just look it up in the table. If it needed a cosine of some angle that was not an integer number of degrees, then it could look up the next two values and then use linear approximation in the interval. So in this way, the applications could speed up their calculations by noticing that an expensive calculation, the calculation of a sine of an angle in this case, or cosine or whatever, could be pre-calculated, calculated only once. You can store the value. And the next time you need the value, you don't need to perform the expensive computation again. You can just look up the stored value, and this can be faster. So in this case, the application could have maybe a 3 times or 4 times speed up, and often this was enough to go from 6 frames per second to 24 or 30, and suddenly the game started to play smoother on worse hardware. So that was exactly what they needed, and this was kind of an improvement. And in some sense, there is no bigger trick to memoization. It is still the same idea. We don't need to perform the same expensive calculation twice. We can just do it once, store the value, and the next time we need the output of the same calculation, we can just look up the value instead of computing it again. This is the whole idea. But it turns out that our problems are kind of more difficult, and the correct application of this idea is kind of harder to see. So let's talk about that in more detail.
Hey, misof, sorry to interrupt. Are you showing anything on the screen right now? I mean, it just went black, and members are not able to see the screen. Do you want to reshare?
No, I'm currently not showing anything on the screen, but you should see at least me on the video. Do you see me?
Yeah, we see you.
Yeah, okay. I'll start showing something on the screen when it becomes relevant. Okay. So currently I have post screen sharing, but later on when I'm doing the coding or have something to write, then I will start sharing the screen. Then we'll check whether everything works. Thanks, Harshit.
Sure. Thanks.
Okay, so before we actually start blindly applying memoization, there's one thing we have to realize. And this is that there is a difference between computer science, or maybe more precisely programming, and mathematics. Mathematicians, they love to claim that computer science is just a branch of mathematics, but in some sense it is, in some sense it isn't, and there are some flavor differences at least. And one of these flavor differences is that there are objects called functions in mathematics, and there are also objects called functions in programming. And the same name denotes a kind of a different type of objects. So if in mathematics, if you have a function, a sine, cosine, factorial, whatever, these functions have exactly the property I mentioned before. The output value of the function is exactly defined just by the input parameters and nothing else. The factorial of 47 will be the same value tomorrow, day after that, 100 years in the future. In programming, if you have a function, there are very many different factors that can influence the output of the function. Not just the arguments of the function, but there's all kinds of things. So for example, inside the function, we could use random. We could have probabilistic functions that flip a coin, and based on the coin, they change the value of the return. We could have input from the user inside the function, and this also will influence what the function does. The function can depend on environment. So for example, if you have the exact same function, but one of the users is running it in one language, another one is running it in another language, and the function is calling some library function for string sorting. The string sorting and collation and everything could be influenced by the local settings, by the language that is being used by the user. And most importantly, what matters in programming is also the scope. So the function doesn't only have access to its arguments. The function in general, at least in most of the imperative programming languages, has access also to all of the variables that are in higher scopes. So in particular, it can access global variables. And if the global variables change between different runs of the same function, then again, this can lead to the function producing different output values. So we can apply memoization also to functions in our programs. But when we are doing that, we need to make sure that the function in the computer science sense is also a function in a mathematical sense. So we do want to have functions such that the output value of the function only depends on the arguments the function received and on nothing else. If we can do this, then we can apply memoization. So instead of computing the same value of the function multiple times, we can actually just compute it once and store the output of the calculation. And when I get to some examples, we will see how strongly this can help. So let's actually do that right now. And let's start writing some code, and let's start solving some very easy problems. So I'll try to share a whiteboard with you to start. And we can take a look at one of the very basic and standard textbook problems, which are the Fibonacci numbers. Okay, so Harshit, is everything all right now? Can we see the whiteboard?
Yeah, I'm just giving a last check on the YouTube stream to see if it is visible on YouTube. Because of the screen size, it was not visible on the terminal window was not visible on the YouTube recently. So you can begin, and I'll just take and stop you if we don't see the screen over there.
Okay, great. So let's start with a textbook example of Fibonacci numbers. So Fibonacci numbers are a mathematical sequence with a very well-known definition. So we start with the Fibonacci number 0 being equal to 0. Fibonacci number 1 is 1. And all of the following numbers, the next number is the sum of the previous two. So the next numbers in the sequence would be after the 0 and the 1, we have 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 13, 21, and so on. So this is a well-known sequence, and more importantly, what we have here, the mathematical definition, is something that can directly be translated into a program. So if you just take the mathematical definition of this sequence and implement it as a recursive function, you will get a program that computes the Fibonacci numbers just by using the definition and nothing else. So let's try sharing the window, and I will start actually implementing this solution so that we can see it. Okay. So how about now? Do we have a console, and can we see it in all of the streams?
I can see it here. I'm just gonna go back and check on YouTube, and just a minute, and we'll be able to confirm. There is a slight delay when it comes to YouTube, so yeah, we can see it on YouTube. All good.
Okay, so let's begin. So the Fibonacci number n is computed as follows. If n is equal to 0, the answer is 0. Else, if n is equal to 1, the answer is 1. And in all other cases, the answer is the previous Fibonacci number plus the Fibonacci number before that. And we return the answer. So this is the function. And now we can have a main body to test the function. So we will take the value n as the input from the user. And we will print the value of the nth Fibonacci number. So if we give it the value 0, it will output 0. If we give it the value 1, it will output 1, 2, 3, 4, 5, 6, and so on. And it seems to correctly compute the values of Fibonacci numbers. So this was a step we could do without any thinking. We just took the mathematical definition of the Fibonacci numbers, and we produced a recursive function that is implementing this exact definition. It has the special cases for the beginning of the sequence, and it has a general case for computing the next step of the sequence. So what is the problem with this particular way of computing the Fibonacci numbers? The problem starts being apparent when we start computing the Fibonacci number 30. And suddenly we can see that the output is not instantaneous. Actually, if we measure the running time, we can see that in my case, on my machine, it's like a quarter of a second until it computes the Fibonacci number 30. Oh, sorry. Fibonacci number 31, half a second. Fibonacci number 35, almost 3 seconds of computation. Fibonacci number 40. And now we can see that the program is running, and I have the time to take my cup of tea and start sipping and thinking about other things while I'm waiting to get the output of the program, because it starts to be quite slow. All right, sooner or later we will get an output of the program. Let's get back to it later, and let's switch back to the whiteboard. What's going on, and why is that a problem? What's going on here is that the program is in some sense stupid. The program is doing the same thing multiple times. Let's see what happens. If we call, for example, the program with the argument 5. So, hey, program, compute me the 5th Fibonacci number. What the program needs to do is it needs to compute f4. And later, when this function returns, it also needs to compute f3. The recursive call to f4 needs to compute f3, and it needs to compute f2. The call to f3 needs to compute f2, and it needs to compute f1. And the call to f2 needs to compute f1, and it also needs to compute f0. And this call to f2 also needs to compute f1, and it needs to compute f0. And this call to f3 will also call f2. It will also call f1, and so on. f1, f0. So what have I drawn here is called the recursion tree, and this is showing the exact function calls that will happen during the execution of our program. So if we call our function with the value 5, so the user has entered 5 from their keyboard, this is the input value we have read, and now we call the function f with the argument 5. What will happen is the computation will proceed as follows. We call f5, f5 will call f4, f4 will call f3, f3 will call f2, and so on. So each time we call the function, so it does all of the steps we had in the program. Is 5 equal to 0? No. Is 5 equal to 1? No. So it is not the one of the basic cases. It's the recursive case. And in the recursive case, I need to make a recursive call, f4, and then I need to make a recursive call, f3. So the computation will proceed as follows. Something like that. So we are computing values of the Fibonacci sequence in some specific order that was implied by the recursive definition. And what we can notice is this solution is actually violating one of the two rules of designing efficient algorithms. This solution is computing the same thing twice. It's computing the value f of 3 here. It's computing the value f of 3 over there. It's computing the value f of 2 here, but also here, but also here. It makes the recursive call of f1, 1, 2, 3, 4, 5 times. And we can actually check that this is happening by introducing some debug outputs into our code. So let's do just that, and let's check what's going on in the code. In the meantime, we actually got the value of the 40th Fibonacci number. It's 102 million, and it took 35.3 seconds to compute. So once again, what's going on here? Each time we call the function f with some argument n, it compares the value of n to 0 and 1, which are the cases when it can directly give us the answer. And then if that didn't happen, it performs two recursive calls. It calls itself with the value n-1, and it calls itself with the value n-2. So let's add a very simple debug statement. About the value with which we called this particular function. So if we now call the function, let's say, with the argument of 5, which is what we had on the whiteboard, we see exactly the output that corresponds to what I draw. We call f5, f5 has called f4, that has called f3, that has called f2, that has called f1. F1 has directly returned the value of 1. So we return back into the call of f2. F2 has then called f0, which returned 0. 0 plus 1 is 1, so f2 returned 1. We got back into the f3 and so on, and we got all of these calls. And we can actually, magic of the Linux command line, we can actually take the output and count how many times each of the lines appears. So for the input of 5, we got the function call of f0 3 times, function call of f1 5 times, 3 times twice, once, and once. If we call the computation of the 10th Fibonacci number, the values are starting to be bigger. If we are computing the 30th Fibonacci numbers, we can see that the program is doing quite a lot of work. So the value of f0 was computed 500,000 times. The value of f1 was computed almost 1,000,000 times. The value of f2 was computed 500,000 times also. So what this program does is it computes the same thing over and over again unnecessarily, because this is a mathematical function. This is not just the function in the programming sense. This is a mathematical function. If we look at the program, the body of the function, absolutely nothing else influences the output, the answer value, only the variable n and nothing else. So let's go ahead, let's be smart, and let's make sure that the function doesn't compute the same value multiple times. What will happen if we do so? I'll start with a semi-lazy way of doing this, and the semi-lazy way in Python is using a dictionary, which is implemented as a hash map. So this is not the asymptotically best way of doing it. The best way would be using an actual array, which has constant time access because the keys are small integers, but we'll get to that later. For now on, let's start with something very simple. So we have a global dictionary called memo, and what we will do inside our function, I'll remove the debug output at least for now. The very beginning of the function will be the check. Is this something new, something we haven't computed before? Or is this something we have actually seen before? So if the value n is already a key in the memoization table, we have stored the correct value and we can return it. Otherwise, this means that this is the first time we see the argument n, and the body of the function is executed to compute the value and to do the recursive calls if necessary. And then at the end of the function comes the second step. And the second step is again purely mechanical. There is no thinking, there are no different cases in different situations. This is just mechanically, we have just computed the value of the nth Fibonacci number. And to make sure we are not computing it again in the future, just store it in the memoization table. So before we actually return it from the function, we store it in the table. So let's check what happens if I compute the value of the 30th Fibonacci number again. We got the same result as before, which is quite pleasing because it means that I probably didn't introduce any bugs. It's 800,040. And what changed is the time of the computation, which is now much faster and becomes apparent when we are computing the 35th or the 40th Fibonacci number. 40th Fibonacci number before took 30 seconds. Now it's still 1/100th of a second, which is essentially the time needed to load the Python interpreter into memory. So before, it was completely hopeless trying to compute the Fibonacci number 50. Now if we do 50 or 100, we get the outputs really quickly. And we can see that the 100th Fibonacci number is quite big. And moreover, later on, we will think a bit more precisely about what happened to the time complexity of our program. And producing this number cannot be done if we are computing this number one at a time and incrementing it by one each time we do some step of our program, because this number is several orders of magnitude bigger than any number of steps we can do in a reasonable amount of time. So let's go back to the whiteboard and let's check what happens if we apply memoization. So the computation of our function started exactly as before. We started with a call to F5. The call to F5 produced the call to F4. The call to F4 produced the call to F3. That one produced the call to F2. That one produced the call to F1. And the call to F1 did not just compute that the value of the first Fibonacci number is 1, but it also stored the value in the memoization table. So we already know that for the input 1, the output is 1. When we got here, we also got the information that for the input 0, the correct output is 0. We returned back to the Fibonacci function with the argument 2. It now computed the sum of the two values it got. 1 plus 0 is 1. And before returning the value, we stored it in the table. For the input 2, the correct output value is 1. We return back here. And now F3 did call F1. But what happened in case of F1 is that instead of running the body of the function, we just looked into the lookup table and we could see that, yes, we already computed the correct output for F1. It is 1, and we just returned it. So when we returned it, the function with the argument 3 could now compute that F2 was 1, F1 was 1, 1 plus 1 is 2. So for the input 3, the correct output is 2. And as we proceed on, the call for F4 will call F2, but we have already computed that value, and we will now learn what is F4. And then the call to F3 will already computed the value, and we return it back. So all of the green boxes now show the places when we could use memoization, and we could skip the rest of the computation. So in the first case, we didn't skip anything, but the second time we used the memoization when we directly access the value of F2 instead of recomputing it again. The red circle shows the part of the computation we saved. And in the third case, this is the part of the computation we saved. So what happened to the time complexity of our program? If we are counting each arithmetic operation as one step, so each addition is counted as one step, then in the case of Fibonacci numbers, the number of steps grows exponentially in n if we are just using the simple recursive definition. This is because the number of steps is actually proportional to the Fibonacci number we are computing. We are just assembling the number from ones and zeros, and each of the inner nodes is just computing a sum of what it got below. So the value we are returning from the root of the tree is the sum of all of the values returned in the leaves. And in each leaf, we are returning just the 1 or a 0. So the number of leaves is at least as big as the output value. And we know that the Fibonacci numbers are growing exponentially. The factor of the, so the base of the exponential function is called the golden ratio, and it's approximately 1.6. So the time complexity of the original program was exponential in n. It was 1.6 to the power of n. And this is why we could see the growth in running times. The 30 Fibonacci number was half a second, and each of the next ones was a constant factor more than before we applied memoization. As soon as we applied memoization, what we got is that each individual value is only computed once during the run of the program. So exactly once we compute, we learn the value of F0. Exactly once we learn the value of F1, F2, all the way through Fn. So we have exactly n values. And for each of these n values, the body of the function, of the recursive function, is only executed once. And the execution of the body of the function takes constant time. So we could say that the program is linear in n. So we are going from exponential in n to linear in n. And I already admit that I'm deceiving you a little bit. So let me show you what I mean and where I was deceiving you that little bit when I was now talking about the time complexity. So let's share the console again. And let's see what happens when we go beyond 100. When we go beyond 100, we go to 1000. What we get is an obscure Python error, which says recursion error, maximum recursion depth exceeded. What happened here is that, as I was mentioning, the computation of the function, we are using recursion. We are using functions that call itself. And in order to execute recursion, computer programs are at least also the Python interpreter, are using what is called a stack. So each time we need to execute a function from a function, we need to create a new record on the stack where we say these are the new arguments. This is how you report your return value. This is where you continue computation when you return from the function. So the data like this has to be stored for each and every recursive call. And each operating system has its own internal limit on the size of the stack. And also Python interpreter is adding its own on top of this. So if we are getting an error like this, we need to get rid of the internal Python limit first, which is done by a call from the sys function. So we import the sys function, sys library, and set the recursion limit to something stupidly large. So now we can get the value of the 1000 Fibonacci number and the 10,000 Fibonacci number, and we have quite a carpet of digits, and 100,000 Fibonacci number has now exceeded also the capacity of the internal stack in Linux. So I got a crash again, but I can remove also the limit on the internal stack in Linux. And then we will get the nice carpet of digits that represents the 100,000 Fibonacci number. So this is it, the 100,000 Fibonacci number computed in less than half a second. So this is a huge upgrade. Previously, when I was talking about pre-computing the tables of cosines, the improvement was a factor of 4. It was just improving a constant factor. But what actually happens in algorithm design is that applying memoization in correct types of problems can improve your time complexity from exponential to polynomial, as it happened here. And it's quite surprising, quite stunning how much of a speed up it can do. Before, we could compute the first 30, 35 Fibonacci numbers, then we got stuck. Now we can compute the 100,000 in a fraction of a second. I said I was deceiving you when I was talking about the time complexity. And the point where I was deceiving you is at the beginning, I stated kind of very quickly and without too much explanation that I will assume that each arithmetic operation, each addition is a constant. And this is not true. The problem is that as soon as we are starting to work with numbers as big as this one, addition doesn't happen in constant time. The algorithm has to add the two large numbers, and it has to essentially proceed this by the same way we do in primary school, digit by digit, and carries and everything. So actually, arithmetical operations have size proportional, so have time complexity proportional to the number of digits in the number we are operating on. So when we are adding two large integers, we cannot just claim it happens in constant time. What we can tell is, as I mentioned before, we know that the Fibonacci numbers grow exponentially. And this means that the number of digits in the nth Fibonacci number is linear in n. So when we are computing the nth Fibonacci number, then when we are getting close to the end and computing the very large ones, each of them will have on the order of n digits. It's actually n divided by something bigger than 1, so it's the constant is smaller than 1 in the time complexity, but what we are doing is we are computing the values of n Fibonacci numbers, or n plus 1 Fibonacci numbers, everything from 0 to n. We are storing them in memory, and each of these of the later computations is linear in the number of digits, which is roughly n. So the actual time complexity, if we are to measure each and every single step of the processor, would be quadratic in n. And in the previous case, there was also this linear factor, but it was completely negligible in comparison to the exponential time complexity that arises from incorrectly using the recursive function, or not incorrectly, but inefficiently. And this is essentially the main secret. If we are, there is a class of problems similar to what happened here with the Fibonacci numbers, in which we can apply similar memoization with a similarly strong effect. And I will now show one such problem that will be shown not from the side that here you are given a recursion, but it will be shown from the side here you are given a problem. And then you need to think in order to discover where to get the recursion from. So let's take a look at such a problem. So for this problem, imagine that you are Xena, the warrior princess, and you have just saved some prince from danger, and the king is offering you the hand of the prince in marriage. You don't want that, but he's also offering you a substantial reward, which sounds more appealing. And for the reward, you are led into the king's treasure room, and in the treasure room there is a row of treasure chests. The treasure chests have different sizes, and more importantly, different contents. And for each of the treasure chests, you can very easily say the value of the stuff that is contained inside. And this is the actual input we are getting in our programming assignment. So we are given the number n of treasure chests, and for each of them, we are given the value of the stuff inside. So v0, v1, and so on, all the way through v of n minus 1. And our task is to take some of this treasure for ourselves. The king has just one requirement, that he doesn't want to end up completely poor. So he is saying that you can take any set of chests you like, but you cannot take two adjacent chests. So, for example, one possible solution would be to take this one and this one and that one. Another valid solution would be to take just this one and that one. But the solution that would involve taking this and this is not valid because they are next to each other, so we can take only one of them. So how can we approach such a problem? How can we find the optimal way of taking the treasure from this king? And this is the place where we need to think about the problem. And this is maybe the most important lesson I want to give you in today's webinar, how to think about problems like this one. One possibility is to try thinking about complete brute force. This is not necessarily a bad thing. I mean, what we need to here is we are doing some combinatorial optimization. We need to, among all of the valid solutions, we need to select the one that produces the best value. So one possible way of solving this task is iterate over all possible solutions, compute the value of each of them, and take the best one. If you do this, you have one guarantee, which is you have clearly a correct algorithm. You are clearly returning the optimal solution because you have actually tried all of them. And even though in programming competitions, we don't often encounter such problems because we try to focus on designing efficient algorithms, in practice, surprisingly often a brute force solution could be enough. If the number of chests is somewhere around 20 or even lower, then it's perfectly feasible to try all possibilities. And often it's also the easiest in terms of programming time. I mean, if you just need to iterate over all possible subsets of chests and check, is this subset valid? Do I have two adjacent chests or not? And then, is this actually an optimal solution? Is it better than the solutions I've seen before? And you are done. One possible improvement of this solution would be that instead of generating all possible subsets, there are 2 to the n subsets, we can just use some recursive backtracking, and we can just check all of the valid subsets instead of, so we will generate only the valid subsets. We will never try the solutions where 2 of the boxes are adjacent. It can be shown that in this particular problem, this will actually improve your asymptotic time complexity. We'll see it a bit later why it happens. But the main thing I want to highlight here is that there are very different ways of implementing such a recursion, such backtracking. And many people who start by learning backtracking sooner than they get to the area of memoization and dynamic programming, they tend to implement backtracking in a way that's not really suitable here. So the main lesson I mentioned a while ago is to unlearn this and to learn to implement backtracking properly and to think about backtracking in the proper way. So the way that's bad for us is a way when we have a function that doesn't return anything, and we have a global variable that stores the current partially constructed solution, and another global variable that is storing the best solution found so far. This approach is perfectly valid if the only thing we want to do is to do actual backtracking, but the approach is completely useless for memoization purposes, because what we are doing is we are all of the time we are modifying some global variables that are placed outside of the scope of our function. So instead of doing that, we need to start thinking about backtracking as asking questions. So imagine our heroess Xena, the warrior princess, actually standing on the end of the line. So this is her. She's carrying a big sword to intimidate anyone who wants to oppose her. And then she is looking at the treasure chest number n-1, and she's asking a question. Okay, so I want to construct the optimal solution. Should I take this chest into the optimal solution, or should I abandon it and move on? Well, I don't know. So let's try both possibilities. If I decide to throw this chest away, what I get is the same question, but only for the first n-1 chest. So if I discard this one, I get the question, what is the optimal solution for the first n-1 chests? So in this way, I can make a recursive call and ask this question. So I was asking the question, what is the optimal solution for all of the n chests? And I got that in order to know that, you need to know the optimal solution for the first n-1 chests. And now Xena has another option. What if I take chest n-1 to be a part of the solution, to be a part of the set of chests I'm taking away? Well, if I take this one, definitely by the rules of the game, I cannot take the next one. And I'm left with the first n-2 chests. So the optimal solution, in the case when I do take the last chest, is the optimal solution for the first n-2 chests, and plus the value of the very last chest. And again, now we are done. Now we have found a way of computing the solution recursively, of trying out all possibilities recursively. So we can now again move to the console and try to implement this particular solution. So one thing we need to do is we need to read the values of the individual chests from the input. And in our program, these values will be a global variable. And the output of the function we will be later implementing does depend on this global variable. But the main point is that the global variable is a constant. The values don't change during the execution of the program. And therefore, we can regard them as just constants that are accessible from inside of the function. Some purists with experience of programming in real life in a company will now object against using global variables because it's ugly. But I don't agree with that objection, because this is exactly the place where you should use global variables. These are variables values that are actually global, that are actually there during the entire execution of this program. They have the meaning. If we are implementing this as a part of a bigger project, we would have a class for the solver. The values of the chests would be an internal variable of an instance of this class of the solver, and then the method could directly access those as read-only variables during this execution. So it would be pretty also from the implementational point of view. So right now we are just doing a small program with one focused goal, and it's perfectly all right to use global variables in this context.
So we have the values of chests, we have the number of chests, we have read them from the input, and now we are going to do the recursive function. So we have a function solve, and now the important thing is that this is a function that is asking, we are asking a question by calling this function, and the function is answering the question by returning a value. So the question we are asking is, what is the optimal solution for the first k chests? If k is less than or equal to 0, so we don't have any chests left, and I'm doing less than or equal instead of just the equal. We'll see in a moment why it happens. So if there are no more chests, then the answer is 0. And in the opposite case, we are doing exactly the same thought process we had Zena do at the very last box. So we have the first k chests. The last of them is chest number k minus 1, because we are numbering starting from 0. And we have two options. We can take it and we can leave it. If we take it, so let's start with leave. If we leave it, if we don't want this chest, then the optimal solution has value solved of k minus 1. So we are asking, what is the optimal solution for the other k minus 1 chests, other than the one I just discarded? If we take it, we need the optimal solution for the first k minus 2 chests, and plus the value of the chest we did just take, v of k minus 1. So the optimal solution, if we don't take it, is in the variable leave. The optimal solution, if we do take it, is in the variable take. And our answer is the better of these two options, is the maximum of leave and take. And we return the answer. And the actual output we are interested in, the optimal amount of money we can take from the king, is the solution for all of the n chests we got in the input. So this should be a solution. Hopefully I didn't make too many typos. We'll see. Let's create an input file for this solution. So we will have 5 chests to test it on, and the values of those chests will be, let's say, 100, 4, 7, 90, and 13. So in this case, we would expect that by hand that the optimal solution is to take the chest with value 100 and to take the chest with value 90 and to discard all of the other 3. So we expect, if we implemented it correctly, the output should be 190. And I got a typo. I used int instead of len, so let's correct that really quickly. So n should be the length of the array v, not the conversion of the v to an integer. And luckily, that was apparently the only bug I introduced. So we actually did get the value 190. So let's create a bigger input to test the solution, how quickly it runs. So here we have generated an input with 35 values. And computing the solution for 35 different chests apparently takes a non-trivial amount of time, but we do eventually get the output. Let's measure the time for this process. And it looks like it runs for about 8.2 seconds until we get the output. 282,574 is the optimal solution for these particular chests. What's going on here? What is the time complexity of this program? The time complexity of this program is actually quite easy to determine, because what we are doing is the time to process an instance with n chests is essentially time to process an instance with n-1 chest, because we are making one recursive call with n-1 chests, plus the time needed to process n-2 chests, and plus some kind of a constant. So if we express the running time of this program using a recurrence, we get a recurrence that is really, really similar to Fibonacci numbers. The time for n is essentially the time for n-1 plus the time for n-2. And it turns out that, yes, the recurrence does actually solve to something that grows exactly as quickly as Fibonacci numbers. So the time complexity of this particular program is 1.6 to the power of n approximately. So instead of the original suggestion that was just iterate over all possible subsets, and your time complexity will be proportional to 2 to the n, by implementing the recursion that is only trying the valid solutions, the valid solutions are sparse enough, so we got a time complexity that is still exponential, but at least the base of the exponential function is smaller. But we are still making a mistake. What is the mistake we are making? The mistake we are making is that we are violating the rule we mentioned before. We are violating the rule, don't do anything twice. We are calling the same function solve over and over again with the same argument. So as before, let's double check that this is happening by adding a debug output that we are calling the function solve with some specific argument k. Now let's try it on the smaller input first. We see that we are calling function solve with arguments from 5 ranging down to -1. Wait, what? What -1? What is -1 chests? What happened here is that I was kind of clever to deal with a special case. So what happens if we have just a single chest? If we decide to throw it away, we are left with 0 chests. But if we decide to take it, we should just be left with 0 chests as well. But this is a special case, because in all other cases, what we are doing is we not just take this chest, but we skip the previous one. So we decrement the count by 2. And if we have only a single chest, then we are going from 1 to -1. So instead of saying if you got -1, it should be 0, I was handling this a bit later, saying it just here. If you got something below 0, it should be 0. It still means that you have no chest left. But
okay, so sorry to interrupt. Can you make sure you're always closer to the mic?
Yes, sure.
When you move a little bit back, the voice becomes a little bit it gets a little bit faded away.
Okay.
Yeah.
So I'll move the microphone actually a bit closer to myself. That could help.
That should do. Thanks.
All right. So where were we? We were checking out the debug output, and we see that we are computing the value of solve2, and again we were computing the value of solve2, and solve2 here, and solve2 there, and solve1 was in many places, and solve0 was in many places. And as before, we can sort all of them and count how many times each of these debug output appears, and we see that we are calling the function with the exact same argument multiple times. And this is unnecessary. This is wasting computational power, because this is a mathematical function. Nothing changes. If you look at the source code, the only thing we are referencing is the input variable k, and the value in the array v that doesn't change during the entire runtime of the program. So each time we've called the function solve with the same argument, each time we are asking the exact same question. What is the optimal solution for the first 7 chests? And each time we call solve with the argument 7, we are asking this question, and each time this question gets the same answer. So what we can do is get rid of this by applying memoization. So again, before we do that, let's see what happens for the bigger input. So this is an input with 35 chests, and now it will take quite a long time in order to generate all of the debug outputs and sort them and give us the report. But we will see that as the time complexity of the program grows exponentially, also the number of times we call each of the individual functions grows exponentially. So instead of seeing the same function called 3 times and 5 times, we will see the same function with the same argument called millions of times. And this is the source of inefficiency. All right, this is taking ages. Let's break it and let's make the input a bit smaller. Let's go down to 25. So now we should have about 25 numbers, and it should be reasonably fast. So already for 25 numbers, we see that we are 46,000 times we are doing the same work. We are solving the problem for the first 2 chests. So 28,000 times we are solving it for the first 3 chests, and so on. So let's copy the source code into another file. And let's add memoization. Now I'll do it for the correct Python way. I need to look it up in the documentation, actually. Is it max size? I think it's max size. Yeah, it's max size without the underscore. So Python has actually its own decorator, which is called least recently used cache. So instead of doing all of the memoization by hand, if we are lazy and we are using Python, we can also just decorate the function and say that the function has a least recently used cache of input and output values, and the max size is unlimited. And when we apply this decorator, what am I doing? When we apply this decorator, we see that the body of the function is now only executed once for each value, because the first time it was executed, we store the key, the pair input and output in the memoization table. And we got exactly the same output as before, 174,000, but now we got it instantaneously. So we can now generate a really large input, an input with 10,000 chests. And again, we just got the error message about the maximum recursion depth. So we'll just copy. And we see that also for the 10,000 chests, suddenly we got a solution that is instantaneous, because as soon as we apply memoization, what it means that this body of the function is only executed once for each valid argument. So once for each possible question we might ask. And what are the questions we might ask? We will be asking about the optimal solution for 0 chests, 1 chest, 7 chests, 17 chests, and all the way up to n. So we are asking only n plus 1 different questions. And each of these questions will only be answered once. And as we can see, the body of the function, it is doing some recursive calls, but what happens during those recursive calls is counted elsewhere. And directly inside this particular function, we only execute a constant number of steps. So we have a linear number of questions, and each of them is answered in constant time. So what we managed to do here, and hopefully I managed to explain it reasonably nicely, is that what just happened is we solved a problem using memoization. We started from the problem, we did some thinking, we did some coding, and now what we have is a linear time solution for the problem. So even if we had 1 million chests, we could still run the solution we have, and it will still compute the answer in a very short amount of time. And usually when people are learning dynamic programming, the main place where they struggle is thinking about the problem, because even if you are reading many different guides that try to explain dynamic programming, it's kind of explained usually in a monolithic sense. The problem. The problem is too big. You need to approach the problem, and you need to kind of magically see the full solution directly, and then you need to implement the dynamic programming or whatever. And what my approach is doing, and the reason why I prefer to think about the problems this way, is I'm kind of breaking it into several conceptual steps. So what happened here is we took the problem. We started by a very simple idea. Let's solve it recursively by trying all possibilities. And still without thinking, still mechanically, what we said is we will be using this specific pattern of thinking where I'm asking the questions, and the recursive function is a way to answer those questions, possibly by asking other questions during that time. So what I did is I tried to design a recursive function where the recursive function is a function not only in the programming sense, but also in the mathematical sense. And there are patterns how you can think about designing such problems. And one of the most common ones is the one I have shown. So we are constructing a whole solution, which is a subset of chests. And in order to do it in a smart way, what we do is we construct it one step at a time. So we start at the very end, and systematically we make decisions. Do I include this in the solution, or do I discard it? And we can build any valid solution in this way by a sequence of definitions, what to take, what to discard. And if we are lucky, then we will get a situation we just got. So not all of the problems obviously are solvable via memoization, solvable via dynamic programming, but in case they are, and in case your approach actually works, you will often encounter a situation like the one we had here, that you will realize that even though your solution is still exponential because it's trying an exponential number of different possibilities, the problem happened to have such a property that you are asking the same question over and over again. The number of questions you are asking is limited, and they get repeated. And if your problem happens to have this property, suddenly you win, and you win big time, because again, you can do the next step mechanically. You can do it without thinking about it. All you do is you apply memoization. You say that we are not computing the same value twice. The first time I compute it, I store the value, and then the value can be reused in the future. And this is all. So this is how you can solve problems via memoization, and this is how you can break the solution into at least a few different steps, some of which are completely mechanical. And the only actual place so far where we had to do some thinking was the place where we had to design the way we are asking the questions, the way that I start here at the end and I ask, do I take the last chest or do I not take the last chest? This was the place where we had to think, where we had to come up with this particular approach of asking the questions. But other than that, the whole rest of the solution, the implementation, was purely mechanical. We are just doing the same things over and over again in all of the problems we are solving using this technique. So to conclude the beginner introductory part of the webcast, I will now talk about the more traditional way of doing dynamic programming, which is iterative. Iterative dynamic programming is essentially the same thing with some minor differences, but it's more common to see it in solutions. It's more common to see it in editorials to programming contest problems. So how do we go from here to there? How do we go from having a function with memoization to having iterative dynamic programming where we are filling an array one step at a time? This is a second place where we actually need to do some thinking. In some cases, the thinking is trivial and it's over in a second. In some cases, it's not that trivial. The main issue here is that when we are doing memoization, we do not care at all about the order in which the questions are answered, in which the individual subproblems are solved. But when we want to do dynamic programming, when we want to solve, what we are trying to do in the iterative version is exactly the same thing. We are trying to answer all of those questions. What we actually are interested in is only the biggest question, the question about the solution for the whole instance we got as the input. But in order to get there, we already know that we also have to answer some of the smaller solutions. And if we want to do this iteratively, if we want to do this in a for cycle, what we need to come up with is the right order in which to answer these questions. In some cases, like in this one, there is a very trivial and natural order in which to do it. And the natural order is to start with the smallest instances and go up to the biggest instances. And in many, many cases, this is all of the thinking you need to do. If I start with the smallest questions and then continue all the way to the biggest questions, it will have the property I need. And the property I need is that in the recursive solution, with memoization, whenever you needed another value, you just made a recursive call. If the value was already available, you got it immediately. If it was not available, the recursive call triggered some computation to get it. In the iterative approach, we need to make sure that whenever we are trying to answer a question, we already know the answers to all of the smaller questions, to all of the previous questions it may be asking. But once we find such an order, and as I was saying, in many cases, the order is quite natural, all of the process, again, is purely mechanical. And we can actually, and I will do it here, we can actually take the recursive implementation and convert it into an iterative one. So let's copy the original source into another one. And let's try editing that one. So we still read the input in the exact same way. And now we will take the body of the function. And we will just, instead of doing memoization, we will be just filling an array with answers. So we will have an array best. And at the beginning, the array best is initialized with zeros. And now for each, or let's just, in this case, we need to, I'll prefer using a dictionary so that I can have an index of -1. Python array starts at 0, and in this case, I have a function call with a value of -1. So let's do it this way. So we will iterate over all possible values of k, starting from -1 and ending at n inclusive. So n plus 1 is the first value we will not process. And now I will take the exact same source code I had before. So I'm not touching these lines at all. The only difference is that instead of making recursive calls, so solve k minus 1 and solve k minus 2, now when we are doing it iteratively, we know that these values have already been computed and they have already been stored in the array best. So this is that we can directly access the best solution for k minus 1 chests and best solution for k minus 2 chests. And the answer we got is the best solution for k chests. And this is it. And the output of the program is the best solution for all of the n chests. So the main body of the function is exactly the same. The only difference is that instead of making recursive calls, we are just directly looking up the previously computed values. And we can see that when I'm computing the value best of k, the values I need for the computations are best of k minus 1 and best of k minus 2. And these two values have already been computed. So I'm never referencing undefined values. I'm just referencing values that have already been computed and stored. And we can see then when I run the new solution on the big input, it's also as fast as before, and it produces the exact same output as the version with memoization. So
that was it for the introductory part of the webcast, and I will now more freely talk about some bigger, harder versions of applications of dynamic programming and memoization. But before that, let's summarize it once again, what we just saw. So one possible way of solving these problems that have this particular property that is to do it in these 4 conceptual steps. To say that, okay, let's try solving this problem via brute force, and let's be clever about how we are implementing the brute force. Let's do it so that our recursive function is actually a function in a mathematical sense. We are asking a question by calling the function, and the function will answer the question when it computes the answer we need. Once we do this, we now have to do thinking, and we have to design such a function. For some problems, it will be possible. For some problems, it will not be possible. If we are lucky and we manage to design such a function, it may be the case. Again, for some problems, it will be. For some problems, it won't. That you will encounter a pattern like here, that the solution for the entire instance we are interested in is kind of somehow related to the solutions of the smaller instances, and we are asking only a small number of questions, but the questions are repeated over and over again. And if this happens, we are lucky, because now we can do mechanically the next step, just apply memoization. You apply memoization, and like that, you have an efficient solution. If you want to go to iterative version of the dynamic programming from here, you can always do it by doing some more thinking. The thinking is about what is the correct order in which I should solve the individual subcases. And in this order, I can then iteratively do the exact same computation I had before in the recursive solution. So this is the main pattern I like to think about problems. And also, obviously, once you get more experience in this area, once you solve a lot of problems that are solvable via dynamic programming, you will be able to see these kinds of relations easier. You will be able to, for example, directly start by writing an iterative version of the dynamic programming for many problems, and to many people, it may actually come more naturally. I'm not advocating this approach forever. I'm not saying that it's the only correct way of thinking about such problems. I'm just saying that if you are a beginner who is struggling with this in this area, or just trying to learn it for the first time, this particular way of thinking about the problems may be slightly easier, because it breaks this big problem into smaller, more approachable parts. So we now have 2 different ways of solving problems that are kind of the opposite faces of the same coin. So we can solve problems iteratively via dynamic programming. We can solve problems recursively and then apply memoization. Are these ways equivalent? Is one of them better? Is one of them worse? The reality is that these 2 ways are actually incomparable. So there are some problems where the iterative version is superior and you want to do that one. There are some problems where the recursive version is superior. So let's spend some time now thinking and learning about these differences between these approaches. So the one with probably more advantages is the iterative approach. And one of the major advantages of the iterative approach is the ability to save memory. If you are doing memoization, the advantage was that you needed less thinking, because you didn't need to think about what is the correct order in which to answer the questions. This was done automatically by the memoization for you. If you are doing the iterative approach, you need to think about the order. But once you have fixed the order, you know when a value stops being useful for you. So for example, imagine that we will do the very same thing we did here to the function that is implementing Fibonacci numbers. What we will get would be an iterative program that is filling in an array with Fibonacci numbers. At the index 0, we had a 0. At the index 1, we have a 1. At the index 2, we have a 1, and also and so on. And I always take the last two values in the array. I take the sum. I append it as the next value to the array. So this is clearly wasting a lot of memory. Why? Because when we are computing the next value, we only need the two previous ones, and we don't care about the rest of the array with smaller indices anymore. So we can actually do another optimization step after that and take the solution that is filling the entire array and change it, improve it into a solution that is just using a constant number of variables. So we are storing two consecutive Fibonacci numbers in two variables. Then you use another variable to compute the next one, and then you shift everything by one, and you iterate this in a cycle. So instead of storing the entire array, you are just storing the variables you need, and you are discarding the older values you will not need in the future. And this is the difference, that you cannot do this with a solution that uses memoization. We have before I have implemented a solution that recursively computes the Fibonacci number and uses memoization. And this solution will be usable up to maybe several hundreds of thousands. And the bottleneck then will be the memory. We will run out of memory. We will we will still have a lot of time, but the numbers we are storing will not fit into memory anymore, and the recursive solution will stop being usable. At the same time, if you implemented the iterative solution and then did the optimization, if you are just using a constant number of variables, you can get easily to maybe hundreds of millions of digits or something like that. So saving memory is very often important, very often is something we need to do in order to be able to squeeze into the limits. So not just the time limit, but the memory limit is also often a real constraint when we are solving problems via dynamic programming. And whenever there is not enough memory, then you need to think about the iterative approach, and you need to think about the order in which to solve the subproblems, and you need to think about when do I still need to remember these particular values, when can I discard them because they will no longer be useful in the future. We are never going to reference these values again. So doing it iteratively allows us to save memory. And in some cases, doing it iteratively also saves time. In this case, the speed up is only constant, but it's there. So what is the main difference between the computations of the two implementations we currently have here, the chest memoization version and the chest DP version? The chest DP version will be in practice a bit faster than the other one. And this is because both of them are doing the same computations, but in addition to those, the recursive version is also doing some background work on the recursion itself. So we are doing a lot of function calls, and each of the function calls needs a constant number of steps before and something after, so cleanup after the function has returned. So we are introducing more work that is only present in the recursive version. So if both of the versions are kind of equal, then the iterative version is maybe preferable because simply it runs faster. The constant factor is smaller if you are doing stuff iteratively. Also, iterative version is very often cache friendly. So when we are filling the array, we are filling it one element at a time, and we are filling consecutive parts of memory. And this means that the part of memory we need can actually be placed into the processor cache, and this again resolves in speedups. The recursive version can solve answer the questions in any order, and sometimes if it happens to be not so systematic, then it will jump around the memory, and this will also slow down the implementation. So the constant factors are usually better for the iterative version of dynamic programming. And but this is not all, and the recursive version does also have its advantages. And the main advantage of the recursive approach to dynamic programming, to approach it via memoization, is that the set of instances you need to answer, the set of questions that you actually need to answer, is not always full. It's not always dense. There are many problems in which this case in which this set of equations will be sparse. So what this means that there are many possible questions you may ask, but if you start with the so-called top-down approach, where you start recursively with memoization, the questions you will actually answer are only the questions you will actually encounter during the solution to your particular instance, and you will solve only the questions you actually need. And it is possible, and for many problems this actually happens, that you will skip many of the other questions. So you'll evaluate only a subset of all of the possible questions. But on the other hand, if you are doing the iterative approach to dynamic programming, you don't know beforehand which questions will be useful and which questions won't be useful. So in general, you don't have any idea how to skip some of the questions, and you need to evaluate all of them. So when you are doing dynamic programming iteratively, usually you need to go over all possible answers, all possible questions, compute all possible answers to make sure that whenever we are referencing a previous answer, you already have it. So for problems with this particular property, problems where the space of questions you need to actually answer is sparse, it can actually be significantly better to implement the recursive approach, the approach with memoization. And therefore, for a good competitive programmer and also for a good algorithmist in general, I believe it's necessary to be able to implement both types of solutions. There are some kinds of, let's call it patterns, let's call it, like design patterns, how to implement memoization in each of the languages so that you don't forget to do it, and so on. So it always pays off to study other people's code. One of the nice things about our programming competition community is that most of the competitions allow you to view source code after a contest. So find a coder that is highly rated and you like their implementation style, look at their actual implementations, and you will definitely see some kind of syntactic tricks how to make sure that they don't forget about anything, they do memoization in all of the cases, and so on. So if you haven't practiced implementing both recursive and iterative versions of dynamic programming, maybe also the practice contest we will now have running is a good place to try it out on different problems. Okay, and this is just the very beginning of the world of dynamic programming and memoization. And once we get to more difficult problems, once we get to more challenging assignments and more challenging topics, we will see that there is plenty to do with what I described so far is only the very basic way of approaching problems and discovering these possible dynamic programming solutions. But it's possible that a problem may have more than one solution via dynamic programming, and these solutions have different efficiencies. So it matters how you are trying to construct the solution. It matters what questions you are asking. And you can ask questions of type A and get a solution with time complexity and cube, or you can ask questions of type B and get a solution of time complexity and squared. And maybe then you can also use a data structure to improve the solution from n squared to n log n. There are cases in which we are using dynamic programming and we are still left with exponential time solutions. One of the most famous ones is the traveling salesman problem, when we have a country and we want to travel around the country and find the optimal way to visit every place and pay the least on travel costs. This is a type of a problem where we actually don't know any polynomial time solution, and most of the computer scientists are convinced that there is no such a solution. But we can still use dynamic programming to improve a solution to this problem. And this is something I can actually show you next. So I will again switch to the whiteboard we had. And let's talk a little bit about this particular problem. So the traveling salesman problem is a problem where we are given a graph. In some versions of the problem, the graph is complete. In some versions, the graph can be arbitrary. And each of the edges of the graph has some assigned value. The values represent travel costs. And what we are looking for, there are many different, again, versions of this problem. Probably the easiest one is just to look for what is called the Hamiltonian path. So we are looking for a way to visit all of the cities in such a way that we pay the minimum total price for all of the tickets. So the sum of the edges of the path has to be minimal. Again, this is a combinatorial optimization problem. We are looking for some combinatorial object. And among those, we are looking for the best one. So in this case, order matters. So what we are talking about is the order in which we are visiting the vertices of the graph. So each possible solution is a permutation of vertices. And there are n factorial permutations. And each of those can be checked in linear time. So if we generate all possible permutations of vertices and check each of them, we'll get a solution that is approximately n factorial in time complexity. How can we apply dynamic programming to a solution like this? So imagine that you started constructing the solution and you already have some kind of a partial solution and you are standing in some particular city and you are asking the question, where should I go next? So how do we convert this into asking questions and getting answers? The very beginning is that you choose a city where you start. This can again be a part of the input that you start in city number 0, or it can be you can be given a free choice where to start, in which case you can try all possible options. So the very beginning of your solution is that I'm standing in this city, I haven't done anything yet, and I'm asking the question, what is the optimal solution? How can I optimally travel through this entire country? Now, after you have made some decisions, after you did the first few steps of traveling, you can be asking a very similar question. Okay, this red path is what I already did. And now I want to ask, what is the best way to continue? And in particular, a good way of asking this question is, what is the minimum cost I still need to pay in order to get a valid solution? So I'm asking about the future, about the part I haven't constructed yet. And the question is, what is the minimum cost of finishing this solution? What is the minimum cost of edges that need to be added? And if this is everything we did, if the red path is the input for the question and the value of the best solution, best way of continuing in the red path is the answer, then we will find we didn't actually save anything, because we will be asking each question exactly once and we will get the same solution we got before. On the complete graph, it will have time complexity proportional to the factorial because it's trying all possible options. So what can we do better? The important observation here is that if I'm asking the question for the red path, and if I'm asking the question for this blue path, the answer to the first question is exactly the same as the answer to the second question. Why is this the case? Because when I'm answering the question, I do not care about the order in which the cities appear on the red path. The only information I actually need to answer the question is the city where I'm currently standing and the set of vertices that have already been visited, the set of cities that have already been visited by the path. And these are the same in both cases. In both cases, I still need to visit the vertices in the individual green circles. In both cases, in both questions, I'm starting in the same vertex. So both of these questions have the same answer. And this is where I can suddenly apply memoization. This is where I can suddenly answer each of these questions exactly once. So what we needed to do here is not just apply the basic design principle I have illustrated before, but we needed to also think about all of the possible states, all of the possible questions, and try to discover, isn't it the case that some of the states are actually equivalent? That in some of cases, I can actually guarantee that this set of original questions will have the same answer. And if this is the case, maybe I need to rephrase the question. Maybe I shouldn't ask, what is the optimal way to finish the red path? Maybe I should ask the question, what is the optimal way to finish the solution if I have already visited this subset of vertices, and this is the vertex where I'm standing. And in this new case, in this new way of asking the questions, we have roughly 2 to the n possible subsets of vertices times n, which is the maximum number of options for one of them, the one where we currently are standing. So this is the number of states. And for each of these states, I'll be asking the same question over and over again. What is the optimal way of finishing the solution if I'm starting in this particular case? And in order to answer this question, again, this is the part of the solution that is completely mechanical, where we don't do any thinking anymore, because we do just the same thing we do always. In order to answer this question, we'll try all possibilities. What happens in the next step? So in the case of the example picture, in the next step, I have 2 options. I can go either here, or I can go there. In the first case, I will be asking a new question. What is the optimal solution if these, in the purple circle, are the visited vertices, and this is the last of them? In the other case, I will be asking the question, what is the optimal solution if these, in the brown circle, are the visited vertices, and this is the last of them? So in order to answer to the original question, I got 2 new questions, but the new questions are closer to actually being done, because in each of them we added one of the vertices into the set of visited vertices. And in this way, we can already implement the recursive solution that will be trying to answer the question for each possible state. So we have 2 to the n times n different questions we are asking. And in each of those questions, we have at most n options to try and possibilities for the next edge to use by the solution. So the total time complexity of the new solution is 2 to the n times n squared. And this is still exponential. This is still not efficient, but it's much more efficient than the original solution. And factorial becomes unfeasibly large already for n equals to 13 or 14. This solution can be run up to n equals 25 in a second, and up to n equals something slightly above 30 if you have a lot of time. So exponential dynamic programming is also a thing, and it's also a way of solving some kinds of problems more effectively. And as I mentioned before, there is a lot more to it. There is a lot of different optimizations that can be applied to different kinds of dynamic programming. There are ways, systematic ways that appear in many different problems, how to save space, how to optimize the time complexity of special types of dynamic programming. So for example, you have convex optimizations and Knut-Yao optimization and so on, divide and conquer optimization. There are techniques how to take an already efficient dynamic programming solution and make it even faster. There are also problems where the main issue is the design of the actual solution, where it's not easy to see what question you should ask, because if you are asking the directly obvious question, it doesn't lead to a dynamic programming-based solution. You have to ask a question that is somehow different. You have to modify the problem first to discover the particular property that allows a problem to be solvable via dynamic programming. All right, then. I think this webcast already took over an hour and a half, and I don't know about you, but I'm quite exhausted by all of the talking I did. So I think this is a good place where to conclude the webinar for today. Wish you good luck in solving the practice problems we prepared for you in the practice contest. And well, thank you for your attention. I'm very pleased that the amount of people that registered to watch this particular webcast. I hope you enjoyed it, and I would be pleased to hear all kinds of feedback you have, what you liked, what you didn't like, whether you want a more advanced version in the future, and for the more advanced version, what topics would you like to hear, and so on. So if you have any feedback, there are plenty of ways to reach me, so please let me know what you thought about the webcast, whether you enjoyed it, and what you want to see in possible future editions if we do any. Okay, I think we still have some questions. Okay, so before we actually conclude the webinar, we have a bunch of open questions, so I will just scan through those and say a bit about a few of them.
Yeah, I actually, you almost answered all of them on the webinar, but
Yeah.
these ones were left, so I just kept them here.
Okay, I'll just check whether there's something I can very quickly talk about. Okay, so I mentioned the least recently used cache in Python. This is a function decorator that can be used in Python. And if you look it up in the documentation for Python, it is in the functools library. It's very nicely described what it does. And it does essentially the same thing I did manually in the previous program. So it introduces a memoization table, and it's storing all of the inputs and produces the output. So it kind of, you can imagine it as taking your function and wrapping it into another one that is first doing the memoization, the checking, and if it hasn't seen the value yet, then it calls your function, and then it stores the answer before you get it. So it does mechanically exactly the same two things I did manually in the previous solution. And as for the rest, I think I already tackled those in some ways. So once again, everybody, thank you for your attention. It was a lot of fun for me, and hopefully you enjoyed it. So see you some next time.
Thanks, Misof. Thanks a lot for your time.